Okay, good afternoon. What did we do before the Pentecost break? Well, we defined the domain. We started to define the domain for all the Haskell expressions. So the idea of the denotational semantics is we want to map every Haskell expression to some mathematical object, and we know how to do this for objects of predefined types like integers and booleans and floating point numbers and characters. We know how to deal with tuples, but the remaining challenge was how to deal with user-defined data types. So what happens if we have a user-defined data type like this? So it's a new data type. At first we just looked at monomorphic types, so no type variables. So the type constructor just is the new data type, and there are several data constructors, constructor 1 to constructor k. And constructor 1 is the data constructor which takes n1 arguments of these types and gives you back a new object of this type over here. Another question was, to what objects do we want to map the expressions of this new type construct? Well, and the idea was, let's look at each data constructor separately. So I mean, this is more or less the same as the Cartesian product of this type and this type and this type and all the argument types. And whenever we have such a Cartesian product, we map it to the Cartesian product, but we add an additional bottom element. We use this lift, and we mark these objects by the name of this data constructor. And we proceed similarly for all the data constructors, and then in the end, essentially we unite all these objects, but we identify all the bottom elements, and this was called the coalesced sum. So the domain for this data type would look like this. For objects that are built with this constructor, well, these expressions would be mapped to objects from this domain. So D11 should be the domain for type 11, and D1n1 should be the domain for type 1n1. And this, in the end, is a tuple of length n1 plus 1, because the first argument is the name of the data constructor. We use this just to mark these objects to make sure that everyone notes that they are built with this constructor over here. And we do this for all the data constructors, and then we unite them, but the bottom element of each of these subsets is identified. So let's do this in an example. Let's look at this example where we define a data type for natural numbers. So there are two data constructors. One is 0 and the other one is suc. Suc takes an argument of type nuts. 0 takes no argument. And of course, here we have the additional difficulty that this is a recursive definition. So we introduce a new data type called nuts, but we use it in its own definition. Now, if we follow this definition above, then the domain for nuts would look like this. It would be dnuts. And dnuts, what is that? Well, these are all the objects that correspond to this first data constructor and the objects that correspond to the second data constructor. So how do we do this? Well, we take the data types, the domains for the argument types, so the domain for nuts is dnuts, and we add an additional element to the tuples with just the name of the data constructor. So here we have pairs consisting of the name suc and the value from dnuts, and here we have just 0. We lift both of these subdomains by adding an additional bottom element, and then we unite them and identify the bottom element again. And now this recursion problem, well, that recursion problem occurs here again because we define dnuts, but dnuts occurs in its own definition. And whenever something like this happens, then in the end we search for a kind of fixed point. So we look for the least solution, the smallest domain which satisfies this equation. So which satisfies the equation that the domain itself is identical to the thing on the right-hand side. And it turns out that the smallest domain that satisfies this looks essentially like this. So the smallest element of this is bottom. I mean, here we have a bottom element, there we have a bottom element, and we unite them and identify the bottom element. So this is the smallest element of dnuts. Now, what are the next bigger elements? Well, here we have an element 0. So 0 is in dnuts, which we find here, and 0 is more defined than bottom. And here we have elements that are pairs. The first component is suc, and the second component comes from dnuts. Now we know already that bottom and 0 are in dnuts. So suc bottom and suc 0 are also in dnuts. So here we have suck bottom, there we have suck 0. And instead of writing them as tuples, it's often more convenient to write them as terms because, well, then they look more familiar to us. So we have suck bottom and suck 0, and I use this term notation. And, well, you can see how the definedness relation is defined here. So suck bottom is a bit more defined than bottom. And now what are the next more defined elements compared to suck bottom? Well, we can replace bottom either by 0 or by suck bottom. If we replace bottom by 0, we arrive at this element. If we replace bottom by suck bottom, we arrive at this element, and so on. And so you can see that this is the domain for D nuts. And at the very end up here, we have an element where suck is applied infinitely many times to bottom. And indeed, the domain also has to contain this element, because otherwise we will not have a complete partial order, because there would be a chain, namely this chain here, this infinite chain. And for every chain, there must be a least upper bound. And so to have the least upper bound of this infinite chain, we need this additional element as well. And now, indeed, these are all the objects that we need for expressions of type nuts. And in this example, indeed, for each element here, we can come up with a Haskell expression which has this object as its semantics. So, for example, if you want to define a Haskell expression which has suck bottom as its semantics, well, how would that look like? That would look like this, for example. So if I define something like this, then clearly bot has the semantics bottom. And if I have the Haskell expression, so let's say this is the definition of bot. And if I now consider this expression suck bot, well, then obviously the semantics of this will be suck of bottom. And if I want something with the semantics infinitely many sucks applied to bottom, I could define something like this. So inf equals suck of inf, and then inf has the semantics infinitely many sucks applied to bottom. So indeed, for each element from D nuts, there is a Haskell expression which has this element as its semantics. So this is we really need all of these elements in order to define the denotational semantics of Haskell expressions of this data type. Now, what happens if we have polymorphic types? So let's look at lists. Let's define the data type for lists ourselves, and this is typically a polymorphic type. So how would we define this? Well, we would say there's a new unary type constructor list. So list takes some other type as its argument, and if this is a type, then list A is again a type, namely, well, it stands for the type of lists where the elements are of type A. We need two data constructors to construct lists, one for the empty list. We can, for example, call this nil, and one for non-empty lists, which we could call cons. So cons takes two elements, one of type A and one of type list A. Now, what is the domain for list A? Well, let's first look at the domain for something monomorphic. What is the domain for list nuts? Now, list nuts clearly is a data type. It's the data type of lists where the list elements are from the type nuts. So how would we construct this? Well, we would do this as we did it on the slide. So we would look at the domain for elements that start with nil. Well, these are either nil or bottom. And what about elements that start with cons? Well, here we take three tuples, where the first component is the name of this data constructor, so the name of cons. The second component would be the semantics of this, and in the case where we have list nuts, this would be an expression of type nuts, and so its value, its meaning comes from the domain for nuts. So it would come from D nuts. And the last element would come from the domain for list nuts. So from the domain of list nuts. And well, this is again a recursive definition, so we would take the smallest domain that satisfies this. So D list nuts is the smallest domain satisfying this equation. So let's think about how this domain could look like. Here I forgot bottom. So what are the elements in there? So clearly bottom is in there. And here we take the coalesced sum of these two things. So what is in there? Well, bottom is in there because bottom is here, bottom is there, and in the union there is again bottom, and we identify these two bottom elements. So the smallest element of this domain will be bottom. What will be the next bigger elements? Well, if we take something which is bigger, then it comes either from this set or from this set. If it comes from this set, there's not much more, there's just nil. So something that is a bit more defined than bottom is nil. Or it comes from this set, and if it comes from this set, it has to start with cons. And if we want to take something which is as small as possible, well, we take cons, we take the smallest element of D nuts, which is bottom, and we take the smallest element of D list nuts, which is also bottom. Well, here's the bottom element of list nuts, here's the bottom element of nuts. So the smallest element here is cons bottom bottom. Now, if we want to check what are the next more defined elements, well, this is already completely defined, but this is not completely defined, so this can get more defined. So how can it get more defined? Well, one possibility is we could replace this first bottom by something that is more defined. This was the bottom element of D nuts. If we want to make this more defined, we can replace it by either 0 or by suck bottom. So if we replace the first bottom by 0, then we have cons 0 bottom, so this is more defined. Or we have cons suck bottom bottom. And the other possibility is to replace the second bottom. The second bottom is the bottom element of D list nuts. And, well, the next more defined elements of D list nuts are nil and cons bottom bottom. So here we would have cons bottom nil and, well, that doesn't fit over here, cons bottom bottom. So in the next hierarchy, we have 4 elements, this, and this. And of course, now this moves on higher. So there are many more defined elements than that. And finally, in the very end, up there will be an element. So there will be a top element, and this top element, which doesn't fit here, oh, maybe it does fit here. This will have the form cons. Yeah, no, okay, there are many top elements. Let's leave this with 3 dots. So there are many top elements here, including some where cons is applied infinitely many times. But there are several ones where cons is applied infinitely many times. So essentially, what is the domain? The domain consists of all terms that you can construct from data constructors and bottom. The domain consists of all possibly infinite terms that can be constructed from data constructors and bottom. And now what happens if we have polymorphic types? Now we looked at the domain D list nuts, which is the domain for lists where the elements are natural numbers. But what happens if we don't regard list nuts or list bool, but we regard list A? And A is a type variable. So what could that be? Well, if we have an expression which really has the type list A and not the type list nuts, if it has the type list A, then it is so general that it could also be used at positions where you need something of type list nuts, and also at positions where you need something of list bool, because list A is more general than list nuts, list bool, and so on. So if an expression has the most general type list A, then it also has the types, well, list nuts, list bool, list anything. List nuts, list bool, list int, list anything. So there are not that many expressions that have this type. So what expressions, what Haskell expressions could we think of that have the type list A? Well, one of them is nil. Nil really has the type list A, because I can use nil at positions where I need a list of naturals. I can use it also at positions where I need a list of booleans and so on. So this really has the type list A. But for example, cons 0, nil, this has not the type list A. It only has the type list nuts. So this has the type list nuts, but not the type list A. Now, is this the only expression of the type list A, or are there more? Yes? Right, a list which contains only bottom elements. So, for example, if we define bot equals bot, so let's say bot has the type A, and we define it as bot equals bot, then indeed we could say something like cons bot nil. Right, this is the list containing one bottom element. This for sure is also of type list A. And of course the list containing two bottom elements and so on would also be of type list A. Of course we could also say, well, there is some, if I say bot list has the type list A, and I define bot list equals bot list, well, this will have the type list A as well. Or if I define something like inf list, which is cons bot inf list, this also has the type list A, right? What will be the semantics of this thing? So to which element from the domain will this thing be mapped, this inf list? The upper right element. So it will be something of this form. Cons bottom, and this will be applied infinitely many times. So infinitely many times to bottom. So this is cons bottom, cons bottom, cons bottom, cons bottom. And after infinitely many times, we have a bottom, but it takes a long time. So this is something on the upper right, exactly. I mean, on the upper right, there are many strange elements. For example, cons 1 applied infinitely many times to bottom is also on the upper right side over here, which is the infinite list of ones. But of course, this will be part of the domain for list nuts and not part of the domain for list A, because 1 is not of type A. Okay, so these strange elements, they are in the domain for list A. And so how do we get it? Well, we simply take the domain for list nuts, and we take the domain of list bool, and we take the domain of list integer, and we take the domain of list anything, and we take the intersection. Only those things that are lists of any possible type, they can also be in the domain for list A. So we just look at all the domains of the form list of some type for all possible types, and then we take the intersection. So type is an arbitrary type. So we take them all and we intersect them, and then we end up with just those elements that we need in this polymorphic type. So in this way, we can extend this whole thing from monomorphic types to polymorphic types. Okay, so now we define for each data type how the domain would look like, and now we put it all together and we define one big set DOM, and this big set DOM contains all the objects that we might need in the domain for any possible type. So we just unite them all together, and we call this big set our overall domain for Haskell programs. So let's put it all together. So now we define a set DOM which contains all the objects that we might need for the denotational semantics. Containing all objects that are needed for the domain of a given Haskell program. And to make life easy, we do the following restriction. The Haskell program may not contain, so the Haskell program may not contain type synonyms. What are type synonyms? So type synonyms are declarations starting with the keyword type. So for example, you can say, I want an abbreviation. I want to say, instead of list of character, I want to introduce the new abbreviation string. Now this is just syntactic sugar, and we just want to make life a little easier by disregarding this. So if your program contains this, you can easily transform it into a program that doesn't contain this by replacing all occurrences of string by list of character. And then the program is equivalent, and you don't need these type synonyms anymore. So this is really just syntactic sugar, and to make life simple, we disregard it. And to make life simple, we also disregard type classes. Now this is not so trivial to get rid of type classes, but we want to make life a little simpler. So let's assume our program does not deal with type classes, and then we can define this overall domain for all expressions of the Haskell program. And this will be defined in the following definition. So this is the domain of a program. So for a Haskell program as above, so without type synonyms and type classes, Well, what is the domain? The domain are essentially all terms that you can build from data constructors and bottom. So the domain depends on the set of data constructors in this program. So we have to look into the program and check which data constructors are defined here. And that then determines the domain of the program. So for every number n, let con n be the set of data constructors of arity n. So con 0 contains all the data constructors of arity 0 defined in that program. Con 1 contains all the data constructors of arity 1 in the program, and so on. So let con n be the set of data constructors of arity n, and we do this for every number n. And in particular, of course, we might have integers and characters and floating point numbers and so on. And they are all considered to be data constructors of arity 0. So here, all the integers and all the booleans, true and false, and all the characters and all the floating point numbers are considered as data constructors of arity 0. So they are all in con 0. And then what is DOM? Then DOM is the smallest domain satisfying the following. Satisfying the following equation. So what is the domain? Well, the domain has to contain all the objects that we need for the expressions in the program. And what expressions in the program do we have? Well, for example, we have functions in the program. And we have more things, so there's more to come. And what should functions be? So what is functions? Well, functions is the following subdomain. It's the set of all continuous functions from DOM to DOM, lifted. So these angle brackets mean all continuous functions which map an element from DOM to another element from DOM plus bottom. And of course, you see that this is a recursive definition because we have DOM on the left-hand side and we have DOM on the right-hand side. And what we mean is we take the smallest set satisfying this recursive equation. And in this set, we need a set where every chain has a least upper bound. So the less defined or equal relation has to be complete. So we need all the functions. What else do we need? Well, we need tuples. Tuples with 0 components, tuples with 2 components, 3 components, 4 components, and so on. So we need all the tuples with 0 components. What is this? What is tuple 0? Well, tuple 0 is just the set containing the empty tuple and bottom. Because if you have an expression of an empty tuple type, well, it's either the empty tuple or its bottom. There are no more choices. Tuples 1 we don't need because the semantics of a tuple with 1 component is the component itself. So there is no difference between an expression in brackets and the same expression without brackets. But tuples with 2 components, this is something we need. So what are tuples with 2 components? Well, we need not only tuples with 2 components, but also with 3 components and so on. So in general, what are tuples with n components, where n is greater or equal to 2, well, essentially it's just the Cartesian product. So the first component of this tuple is an element from the domain, and the second one also, and the nth one also. So this is the Cartesian product dom cross dom cross dom n times. And lifted. So there's an additional bottom element. So now we have the objects that functions are mapped to. We have the objects that tuples are mapped to. And what else is there? Well, the rest are data types, either user-defined data types or predefined data types like the integers, the characters, the booleans, and the floating points. And how do we get this? Well, let's look first at objects that are built with a constructor of arity 0. So with a constructor like this 0. Or with a constructor from Z or B or C or F. And those objects we put into the subset constructions 0. Constructions 0. And objects that are built with a constructor of arity 1 are put into the set constructions 1 and so on. Constructions 1 and so on. And what is this? What is constructions n? Well, this is just the thing that we defined over here. So this contains tuples where the first component is the name of the data constructor and the remaining components are, well, the domains for the arguments of the constructor. So in constructions n, we have tuples of length n plus 1, where the first element is the name of the constructor. So it's a constructor of arity n. And constructors of arity n, the set of all constructors of arity n is con n. So the first component here is the name of some data constructor from con n. And then we have the n arguments. And the first argument comes from DOM, and the second comes from DOM, and the last one comes also from DOM. So then we have DOM n times, and this thing is lifted. So this crazy set is the domain of all the objects that we need. So every Haskell expression can be mapped to some element from this DOM. And of course, it remains to define this mapping. So I mean, there should be some definition saying this Haskell expression is mapped to that element of DOM, and this other Haskell expression is mapped to this other element of DOM, but that will come in the next subsection. Yes? Which one? This big DOM?
No, in the last one.
This one?
Yes, DOM, yes.
I lifted it here.
Yes, but don't you need something like const times bottom?
Const times bottom?
Yeah.
So, I mean, here, for example, we have, so for example, something like sac, comma, 0. This would be element of constructions 1. Why? Because this is element of con 1, and this is element of DOM. And why is this element of DOM? Because it's element of constructions 0. So this is element of constructions 0, which is a subset of DOM. So again, essentially what this contains are all terms that you can build from constructors and bottom, plus the tuples of these terms, plus functions from terms to terms. And what one should also remark is that here we completely disregard the types. So in this, I mean, this is a rather syntactic definition. So in here we have also some elements that we would not need for the semantics. So here, so DOM also contains elements like, well, if it contains suck 0, then it will also contain something like suck true. Or if you want to denote them like terms, then it's suck applied to true. And these terms are, of course, not needed in the semantics, because no well-typed Haskell expression has this thing as its semantics, which are not needed for the semantics of well-typed Haskell expressions. But that doesn't matter. So DOM contains a bit too much. There are some things in there that we will never need in the semantics, but at least it contains a superset of those things that we need. And if it contains a bit too much, then never mind. I mean, so this mapping that we will define from Haskell expressions to elements of DOM will not be surjective. There will be some elements of DOM that we will never need, but we don't care. Okay, so this is the domain, and now, of course, the question is, how do we define this mapping? So we want really to define a mapping which takes a Haskell expression as input and gives you back an element of DOM as a result. And how this can work, we will look at after I wipe the board. Let's now really introduce this mapping, which maps Haskell expressions to elements from the set DOM. And we do this first for a subset of Haskell, so-called simple Haskell programs, and then afterwards we will do this for more complex Haskell programs. So let's start with looking just at a subset of Haskell to make this simple in the beginning. So semantics of simple Haskell programs. So the idea is we want to define a mapping from Haskell expressions to elements of DOM. So the goal is define a mapping from Haskell expressions to elements of DOM. But if we look at an example, well, for example, a Haskell expression could look like this. Let x be 2 in, let x be 3 in the following expression in plus x2. Now, of course, to define this mapping, well, we will do this in a recursive way. So in order to define a mapping from such a complicated expression, we will try to deconstruct this complicated expression and look at sub-expressions, and then probably look at the sub-expression plus x2 and check, well, what will be the meaning, what will be the semantics of plus x2, and from that we can then construct the meaning of the whole expression. So to define the semantics of a large expression, one will first compute the semantics for the sub-expressions, and then from their semantics we will construct the semantics of the large expression again. One first regards the semantics of sub-expressions. So if we have this expression, let's call this star. So if we want to define the semantics of the expression star, typically we will first look at the sub-expression plus x2. So for this, we will first determine the semantics of the sub-expression here, of this sub-expression plus x2. But if we want to do this, well, the problem is that we have this variable x here. Now, in this large expression, we know what x means because here x has a certain value, namely 3. So if we want to determine the meaning of this expression, then of course we need to know what the variables here mean. So we should not evaluate this expression from scratch, but we should evaluate it in a certain environment where we know what the meanings of variables are. And here the meaning of x would be 3, and maybe the meaning of plus was already defined earlier by some plus equations, and maybe the meaning of plus is addition. So therefore, we need the meanings of variables. So, for example, the meaning of x could be 3 is 3, and the meaning of plus is the addition function. And so the idea is we should not evaluate expressions on their own, but we should evaluate expressions in a certain environment. And an environment is just something that tells us what the variables mean. So an environment is just a mapping from variables to elements from the domain. So we need an environment or a context. We need an environment which give us the meanings of variables. So in other words, an environment. So an environment, we typically denote these environments by Greek letters like rho. So an environment rho simply maps variables to elements from DOM. Maps variables to elements of DOM. And then what we want to know is what is the meaning of a certain expression like this in a certain environment. So here, for example, rho of x could be 3, and rho of plus could be the addition function. And then our goal is to determine the semantics of a certain expression in a certain environment. Is to determine the semantics of an expression exp in a certain environment rho. So we need both the expression and the environment, and then we can find out what the meaning of this expression is. So let's define environment formally. So what is an environment? So if we have a Haskell program, and this Haskell program has the domain DOM, then an environment for this Haskell program is some mapping from variables to DOM. So an environment rho is a partial mapping, so it's not defined on every variable, but it will only be defined on finitely many variables. Is a partial mapping, so it's a function from the variables to DOM, which is only defined for finitely many variables. So for most variables, it's undefined. These are the variables that are not defined in the program. But for some variables, it is defined, and your program text is finite. And therefore, in every program, you have just finitely many variables whose value is defined, and for all the other infinitely many possible variables, their value is not defined. So it's a mapping which is only defined for finitely many variables. For finitely many variables. And let n denote the set of all possible environments for a program. Be the set of all possible environments for the program. And to denote these environments in a concise way, we often use the following notation. So for an environment rho which is only defined for the following variables, for the variables var1 to var_n, and where, well, var1 is mapped to some element d1 of the domain, and var2 is mapped to some element d2 of the domain. So each var_i is mapped to some element di for all I between 1 and n. There we often write that rho is the following mapping. It maps var1 and var_n to d1 ... dn. So this should be a notation saying that rho is a mapping that only concerns these finitely many variables. And the first one here is mapped to this first element of the domain, and the second one is mapped to the second element of the domain, and so on. So this is just notation, and you can see it looks a bit like substitutions. Well, because this only does something for finitely many variables. And what we still need is, I mean, sometimes the environment changes. So if you look at this expression over here, before this let expression, there's some initial environment where probably plus is defined and a lot of predefined functions are defined. But as soon as one enters this let expression, the environment is extended because now x is defined as well. So at this position, plus is defined because it was defined earlier, but x is now also defined because it was defined over here. So here we have a different environment, which is like the previous environment, but now x has the value 3. So it must be possible to modify these environments, or in particular to extend these environments, to define additional variables. So x is defined here, but it was not defined before, and after this let expression, again, x will not be defined anymore. It's only defined inside this let expression. And so to modify these environments, to extend them, we need an operation to do this, and I will denote this by the plus symbol. So we can extend environments, and we write rho1 plus rho2 for the environment which results from row 2 by extending it by row 1. So for the environment which is like row 2 whenever row 2 is defined, whenever row 2 is defined. And when row 2 is not defined, then it behaves like row 1. Otherwise, it is like row 1. So in other words, what that means is the following. If I want to know what does this environment do, so how does this, to which elements does this environment map variables? If I apply it to some variable, then I first check, is row 2 defined on this variable? So was this variable already defined in row 2? And if yes, then nothing changes. Then, well, this new environment does the same as row 2. So it's row 2 of var if row 2 of var is defined. And otherwise, it's row 1 of var. And this will be used to extend environments. So the environment that we had before the let expression will be extended here by mapping x to 3. That's what we need this plus operation for. And in the very beginning, when we start with the program, then of course something like x equals 3 is not yet defined, but certain things are already defined because there are a lot of predefined functions in Haskell. I mean things like the plus operation or the times operation or map or whatever. I mean there are many predefined operations. So they are already known in the very beginning. So we start not from scratch, but we start with an initial environment. And this initial environment assigns the predefined meanings to the predefined functions. So this is what we start with, and then this initial environment is extended by user-defined definitions. So we start with this initial environment in the beginning, and this initial environment, we denote this by small omega. So let small omega be the initial environment and what does this do? Well, this maps all the variables that stand for predefined operations in Haskell. It maps these variables to the predefined operations that they are assigned to in Haskell. Which maps all variables that denote predefined operations, denoting predefined operations in Haskell to their intended meaning. So they are mapped to these predefined operations. So for example, in Haskell, this is a variable, and this variable has a predefined meaning. And therefore, omega already assigns this variable to its predefined meaning. And what is the predefined meaning of this symbol? Well, the predefined meaning of this symbol is addition. So this is mapped to the addition function. So what's the addition function? It's a function that is applied to two elements from DOM. So these things are element DOM. And what is the result? Well, if these two elements are really numbers, then they are added. So the result is x plus y. If x and y are integers or x and y are floating point numbers. And otherwise, we make the definition of this undefined. So otherwise it's bottom. So if you apply plus to true and false, then we define it to be bottom. It doesn't really matter what we define it, because in the end we will only define the semantics of well-typed expressions. And in well-typed expressions, plus is never applied to things that are no numbers. But since we have to define this, this environment, we have to give it some semantics. We take the semantics where it's addition if I apply to numbers, and otherwise it's undefined. And on all variables that are not predefined in Haskell, so for example, something like x or so, there this initial environment is undefined. So on all other variables that do not denote predefined operations in Haskell, this initial environment is undefined. So that means if our program consists just of this definition, then here, before we have this let expression x, we didn't assign any meaning to x yet. So here we are still in the initial environment, and the meaning of x is undefined. And here we are in an extended environment where the meaning of x is 3. But the meaning of this symbol has not changed. This still means addition. Okay, so this is the idea of an environment. And now, as I said, we want to define the semantics of Haskell expressions, and we will do this by a function called val for value. Semantics of a Haskell expression exp in an environment row. We will define this using a function val for value. And, well, this val needs two inputs. It needs the expression and it needs the environment. So val goes from, it needs the expression and it needs the environment. So it needs these two inputs, exp and env, and then it gives you back an element of DOM. And we typically denote this as follows. We say val of exp in the environment row. So for historical reasons, the expression is written into these double square brackets, maybe to denote that this is the really important argument, but in reality both arguments are needed. So it's not just the expression, but we also have to say what the variables in this expression mean, and this has to be set by this environment row. And then the whole thing gives me back some element of DOM, so it could be a number or a tuple or a function, something like that. Now, and as I said, to introduce this smoothly, we will not do this for all Haskell expressions at once, but we will start with a subset of Haskell. And this subset we call simple Haskell. So we will see that it is not too simple, so it's still sufficient to express any possible program. So every Haskell program can be converted into a simple Haskell program, but it lacks a number of the nice syntactic features of Haskell. So every Haskell program can be converted into a simple Haskell program, but it might get less readable by that. So it still works, but it looks a bit more ugly, but it's a simple subset of Haskell, and then we'll extend it afterwards. Okay, so, but before doing this, again, I have to wipe the board. So what we will do is, we will first restrict ourselves to a subset of Haskell. Haskell, so-called simple Haskell. And it will turn out that it is not a real restriction, because you can convert any Haskell program into an equivalent simple Haskell program, which does the same. So any Haskell program can be automatically converted into an equivalent simple Haskell program. And so if we define the semantics of simple Haskell programs, we can then also define the semantics of complex Haskell programs by saying, well, the semantics of the complex program is the semantics that we get by first converting this complex program into a simple program and then taking the semantics of the resulting simple program. So by this automatic conversion that we will look at in the next subsection, we can then also define the semantics of complex Haskell programs. So this conversion is possible, and so you might ask, well, why does Haskell contain more than simple Haskell programs? Well, because that makes it nicer to program and nicer to read. So the non-simple part of Haskell is just syntactic sugar. It's syntactic sugar, so it's not necessary to use it if you want to write programs, but it makes it easier to program and it makes it also easier to read. And something like this is called syntactic sugar. So what is the restriction? So what's the difference between full Haskell and simple Haskell? So essentially there are 6 restrictions. The first restriction is a program may contain just one single declaration. Not many, as you might normally write, but just one single declaration. Just one single declaration, and this declaration must have the form just a variable on the left-hand side and an expression on the right-hand side. That's it. Now you might wonder, how can I get this? I mean, normally I write thousands of functions with 3,000 declarations, but believe me, you can squeeze this together into one single declaration, which will of course become rather unreadable because you have to squeeze in the contents of all your 3,000 declarations into one, but it is possible. And well, you can do this even automatically, and we will see how. So just one single declaration. So this is not a real restriction, but it will not increase readability for large programs. The second restriction is just to make life easier. We don't want to treat an extra case. And the restriction is that we shouldn't use the predefined lists, because otherwise you would have to treat this differently all the time because of the special notation. I mean, predefined lists are not needed because we can define lists ourselves. This list A data type does exactly the same as the predefined lists. We don't have the syntactic sugar for denoting things with square brackets, but apart from that, it does exactly the same thing. So no predefined lists. So this is also not a real restriction. It's just that predefined lists look nicer than user-defined lists. The next restriction is if you apply one expression to another, you can normally do this with n expressions. So first expression is applied to the second, the result is applied to the third, the result is applied to the fourth, and so on. And we only want to have expressions consisting of 2 components where one expression is applied to the second one. So no n-fold application of expressions. So we don't want something like this, x1 and then x2 and then x3, xn. I mean, this means this is applied to that, and then the result is applied to expression 3, and the rest is applied to expression 4, and so on. But we only want applications of one expression to a second one. Now that's, of course, no restriction at all, because this is equivalent to adding brackets. So brackets around x1 and x2, another bracket around x1, x2, and x3, and so on. And if you do this, if you add these brackets, then the whole thing is of this form and allowed. So this is really not a severe restriction. The next one again looks rather restrictive. Namely, we disallow the case construct. now maybe you never use the case construct when programming yourself, so this doesn't look very harmful to you. But what you do is you typically use several declarations. If you have one function, you typically write several declarations, several equations for the function, and you use pattern matching. And the main restriction of simple Haskell is that you must not use pattern matching anymore. And this is disallowed by only having one single declaration where we have no pattern matching. And this case construct also does pattern matching. So this allows you to do pattern matching in a single declaration, but we really want to disallow pattern matching. So this is the number 1 and number 4. This is the main restriction. So restriction 1 and 4 means they mean we must not use pattern matching. And that's, of course, that looks rather severe. But as I mentioned, you can transform every program into a simple Haskell program. We will see how. Now, also the next restriction has something to do with pattern matching, because normally if you have lambda expressions, then you may write something like this: lambda pattern 1, pattern n, and then an expression. And this stands for the function which does pattern matching. So if the actual arguments are matched by pattern 1, the first one is matched by pattern 1, the second argument is matched by pattern 2, and so on, then this function can be applied. But we want to disallow pattern matching, and therefore we don't allow these forms of patterns. And so the only lambda expressions we allow, so only lambda expressions of the form no pattern, just a variable, and only a single variable, not many of them, and then an expression. So only these lambda expressions are allowed, and the full general lambda expressions are no longer allowed. So this restriction is also here to disallow pattern matching. And the last restriction is harmless. I mean, typically we have local declarations using let or where, and we don't want to treat them both. So let's disallow where, but we allow let. So no where construct, but let is allowed. So this is easy. This is no real restriction because we can automatically convert any occurrence of where into an occurrence of let. But let is allowed. Yeah, and then of course we have the same restrictions that we had already before, so no type synonyms and no type classes. So to define this formally, we can also define this in a positive way. We can just define this via a grammar. So what are simple Haskell programs? So a simple Haskell program is a program without type synonyms and without type classes, without type synonyms and type classes. And also without predefined lists. Whose only declaration, so there's one single declaration only, whose only declaration is generated according to the following grammar, is generated by the following grammar, So this word needs to be inserted here, but it didn't fit anymore. So how does the grammar look like? I will do this on the slide. So, okay, no type synonyms, no type classes, no predefined lists, and only one single declaration. And how does this look like? So the grammar is rather easy. The program has the form var equals x. So the only question is, how does x look like? What are expressions? And the grammar says, well, expressions could be variables. Okay. Expressions could be data constructors. And we don't handle the case of infix variables and infix constructors separately. We just don't distinguish this anymore. So in the examples, we still use infix sometimes, but in the definitions, we just treat everything as prefix. I mean, that's just syntactic sugar. So an expression can be a variable or it can be a data constructor. It can, of course, be an integer, a floating point number, or a character. And then we can compose larger expressions from smaller expressions. So we can build tuples, that's allowed. We can apply one expression to another, but not n times as in the full grammar, only 2 times. And moreover, as you can see, we cannot use predefined lists anymore. So this expression with square brackets around the expressions was omitted to make life a bit simpler. Then we have if then else, of course, as usual. We have let. We don't have where. I threw this away. And we only have limited lambda expressions of this form, where we have just a single variable after the lambda and then an expression. So this is the whole definition of simple Haskell. And well, clearly it's a subset of Haskell, so this all looks rather like legal Haskell expressions, but we omitted certain parts. And let's first look at this subset and define the semantics for this subset before thinking about the rest of Haskell. So this is the goal. So before we do this, let's look at an example. So let's program something in simple Haskell to get a feeling for what that means. So let's program, for example, the factorial function in simple Haskell. So here's an example, the factorial function fact in simple Haskell. So a simple Haskell program has just one single declaration. So there will be one equal symbol, and that's it. And on the left-hand side of this equal symbol, there may only be a single variable, not more. So I cannot write fact x, for example. That's not allowed. So, okay, since I'm not allowed to do this, I'll just write fact. So the rest has to be on the right-hand side. Now fact should be a function. So the only way I can do this is by using a lambda expression. So I say, okay, fact is a function that takes some number x and maps it to something. And now we want to make sure that this computes factorial. So this something should be, well, something suitable to compute factorial. So what will we do? We will check whether x is less than or equal to 0. Now, if then else is allowed in simple Haskell. If this is the case, then it should be 1. Else, we have to call fact recursively. So we call fact of x minus 1 and multiply the thing with x. So this is, this looks almost like the usual factorial definition. The only thing is that I brought this x to the right-hand side. It's not so surprising. How we deal with pattern matching, that's a different story. I mean, here there is no real pattern matching because we deal with numbers. As soon as we deal with lists, we would need pattern matching. But let's postpone this and let's first look at the semantics of these kind of programs and then discuss how to handle pattern matching. Okay, so what we want is we have something like this and we want to define the semantics of fact. And now, of course, there are some predefined operations in here. For example, smaller equal, or minus, or times. Also these numbers, 0 and 1. So they are predefined. So their semantics is already known. And how is their semantics known? Well, all this predefined knowledge is in this initial environment. So the initial environment knows what smaller equal means. It knows what 0 and 1 and minus and times means. This is just predefined. So the initial environment contains the semantics of predefined things. Contains the semantics of predefined operations. So what that means is that this predefined operation will map less than or equal to the less equal relation, the less equal function. And similarly, this knows what minus means and it knows what times means. So this is predefined. And this initial environment tells us what these things mean. The question is, what does fact mean? And, well, instead of having to deal with, this is a program, and then we have to look at the meanings of expressions in this program. Instead of doing this, instead of determining the meaning of an expression x prime in a program, and the program is now just one single declaration. Programs are pretty short now, they consist of just a single declaration. In a program of the form var equals x. And this is a bit, this is not handy because we have to handle both the program and its expression. So instead of doing this, we could also make this program a local declaration and then merge all this into a single expression and look at the meaning of this expression in the empty program. We can determine the meaning of the following expression. The expression let var equals x in x prime. So instead of regarding programs and expressions, we can simply just regard expressions. This is a single expression, and the meaning of this large expression, of course, is the same as the meaning of x prime in this program. So we just make the program, we turn it into a local declaration. So we determine the meaning of this expression in the empty program. So that means from now on we'll only look at the meaning of expressions and not the meaning of expressions in a certain program. So it suffices to define the meaning of expressions and not the meaning of programs. Expressions and not of programs. So, for example, we would like to find out something like this. To determine the semantics of. Okay, so for example, instead of determining the semantics of fact2 in the factorial program, we instead determine the meaning of we make this fact declaration local, so let fact be lambda x blah 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 in fact2. And so what we want in general is we want that all the variables in here are properly defined. So if a variable occurs in here like fact, then it should either be defined here in this local declaration, or it should be something predefined. But if we just look at fact2 on its own, well, then we would need to know what fact is. And if you just enter fact2 in your Haskell interpreter without defining fact before, it will complain and say undefined variable. So there should be no undefined variables. So we only want to evaluate Haskell expressions in environments which define the meanings for all their free variables. So all the variables in here, they must be either predefined and then they're defined already in the initial environment, or they must have been defined before in this local declaration. To evaluate expressions in environment where all free variables occurring in the expressions are defined. Are defined in the environment. And now, of course, the question is, what does free variable mean? And, well, free variable means all the variables except those that are bound by a let or by a lambda expression. And okay, this we would have to define, but let's do this in the next lecture. So before we stop, one important announcement. So on Wednesday, there will be lecture instead of exercise course. So there will be lecture on Wednesday and no exercise course, but on Friday, there will be exercise course and no lecture. So we just switch lecture and exercise course this time. So Wednesday will be lecture, Friday will be exercise course. Yes?
Is the exercise still due to Wednesday or to Friday?
Okay. You should benefit from this as well. So it should be okay. So let's extend it to Friday then. But you can also submit it on Wednesday.